Wow, there's a nice equation here that we're not going to talk about. But we'll talk about the gist of it. There's different reflectivity numbers that are associated with light, moderate, heavy rain, and whether or not it's hail. So it's called base reflectivity. The color codes, give or take, are about the same no matter what we're looking at on the radars and whatnot. So the way, base reflectivity is going to be showing us for a certain elevation. Here's another little dirty secret that's very important for everyone to be aware of, is that most of the radar apps on web pages and on smartphones don't show base reflectivity, like the lowest elevation base reflectivity from like Lake Charles radar or Slidell or Fort Polk. It actually is a composite reflectivity or a mosaic of multiple radars sites. And so what they're actually doing is, like in the picture here on the right, the storm may show 25 dBz echo near the top, a 50 dBz echo somewhere in the middle, and a 30 down below. So what the radar will assign to this dimension is 50. It shows the highest value. So when we're looking at a comparison of composite reflectivity versus base reflectivity, the exact same storms that we're looking at. One shows a large blob of rain, including in the New Orleans area. They're getting dumped on, according to composite reflectivity. Base reflectivity, there's absolutely nothing going on. There's no green at all. So this is a good example of being very careful, or being aware, I should say, of what you're looking at on your smartphones or on websites, whether we're looking at composite reflectivity or base reflectivity. So composite reflectivity is going to be, in general, overdoing what's really going on out there. I've had a lot of people complain to me about, such and such radar app stinks because it'll show green in my area and I'll be outside and nothing's going on. And I'm thinking to myself, and I'll explain to them, well, that's because they're using a composite reflectivity, and some radar beam is showing the rain that's 10,000 feet above you, and it's being depicted on this overall radar picture. So it's just something to be aware of when you're using your different radar apps. Look at, there should be a settings or something about the app, and it'll tell you exactly how it's doing it. So in terms of recommendations and whatnot, the apps that you want to use would be one that you can pick an individual radar site. So you want to be able to pick, in this case, locally, you're going to want to pick the Lake Charles radar site. And if it's not available, you want to pick the Fort Polk radar site and use that individual site, as opposed to a composite or a mosaic of the multiple sites. The velocity in the picture here, the center of the picture is where the radar is located. And so you can see winds blowing away from the radar, indicated by reds, winds blowing towards the radar, indicated by greens. If the wind is blowing all the same direction, like in this picture here, blowing from southwest to northeast, the radar can't see wind blowing perpendicular to it. So it looks like zero. So the radar beam is going to show the zero winds, when in actuality it's not zero out there. It's just going to show that because it sees nothing. Because the radar beam is, all it's going to see is what's blowing towards it or away from it. It's basically blind for storms going across it. So this is actually, here we are fixing to come up on the 10-year anniversary of Katrina and Rita. This is actually before Rita made landfall. Rita's down here in the eye of Rita, I should say. It's down here off the Cameron coast. And here's that zero line coming up to the coast, curving up into Lake Charles to our radar site and whatnot. So you can kind of see like a little S-shaped for that. So what that actually means is this. At the radar site, number 3, where our radar is located, if you draw a line perpendicular to the zero line, it tells you that the winds are blowing from the northeast to the southwest. Now down here at the coast, east of Cameron, that zero line now is basically north and south. So I know the winds here are blowing east to west. So these are features that you're going to be doing if you're using some of the velocity products. Look at that zero line, draw a perpendicular line on it, and figure out which way is the wind blowing towards the radar and away from the radar, and that will tell you which way the winds are actually blowing at that elevation. And also remember, even though this is one elevation, let's just say the half-degree elevation, here at the number 3, this is very near ground level. Out here at number 2, it's looking at 2,500 feet up in the air. Out here at number 1 in the eye, we're already looking at 12,000 feet up in the air. So you're not looking at the same elevation with a single radar site, single slice of the radar. You're not looking at 10,000 feet everywhere. You're looking at a few hundred feet close into the radar. You're looking at thousands of feet above you for the way you are from the radar. So here's a good example of what we talked about from the last slideshow, the multi-cell cluster, the multi-cell line. This is more of a line. You could argue that's a cluster back here and then more of a line feature there. And you can see this little thin line out in front of it. That's what we talked earlier about the outflow boundary, where you'll notice the wind shift. The winds get gusty as the storm passes through you. So in this picture here, the storm is moving to the south towards my radar site here. So this is the reflectivity. This is the velocity. Once again, you can kind of see the zero line on here. So it's got winds blowing towards the radar, indicated by the greens and blues. So the highest wind speeds are 40 to 50 miles an hour, indicated by these light shades of blue. But we're looking pretty high in the sky, between 1,800 and 3,500 feet. We don't exactly see that over here because of the fact that the angle that the storm's heading towards the radar, it looks more like zero. So the winds over here could be just as high as they are south of the radar, but it looks like zero because it's coming in at that perpendicular angle to the radar beam. So be careful when you're looking at a velocity product and go, oh look, it shows zero winds coming in here to Lafayette. Well, that may be just because of the angle the storm's coming in related to where you're looking at from the radar. So with the radar, Lake Charles radar being off to our west, a storm coming from the north or the south over Lafayette is going to show a zero velocity in this area. The best accurate winds that we're going to see for us is if the winds are either going east or west, if the storm's moving east or west across Lafayette. And of course, most storms around here go like a southwest to northeast flow. So we're never really getting really perfectly radar shot of what the winds look like across the area here. There's actually two different velocity products that we can look at, and you guys can see as well on the internet and whatnot. One's called base velocity, one's called storm relative. And basically, all you're doing between the two is base velocity is just strictly what the radar is seeing, inbound, outbound, towards or from it as it's scanning around. Storm relative, it's subtracting out the speed and the direction of the storm, of whatever it determines that storm is moving on the radar. So if it thinks the storm is moving to the northeast at 20 miles an hour, it's going to subtract out northeast at 20 miles an hour from whatever number and wind speed and direction that it's calculating over here on the right. So like in the picture here, this is looking at the exact, here's Buna, this is over in southeast Texas. On the base velocity, it shows the highest winds pretty far south of Buna, and pretty, two different bullseyes here. Over here, the physical winds a little bit lower on the inbounds, but quite a bit higher on the outbounds, and it's kind of shifted a little bit. So, it is a different product. One has different features over the other. Typically, we use the storm relative velocity feature for the determination of tornadoes. For purposes of just how high the wind speeds are in the cloud itself, we use base velocity. Another feature that we can use the radar for is called echotops, looking to see how high those storm clouds are. So this is just an example of how high in the sky the clouds are. So, these dark orange and reds on here, 40 to 50,000 feet storm clouds. You notice here near Lake Charles, there's nothing going on. Odds are there's storms in the area, but like I said earlier, storms within 20 miles of the radar, that 19.5 degree elevation only goes so high, so it's going to be totally missing storm clouds really close in. In fact, here it is. Here's that zoomed in feature. So, here's a cell to the southeast, a cell to the east. Who knows what the heck's happening over Lake Charles? I mean, there may be something going over Lake Charles. Lake Charles radar is not the best radar to look at for something over the city of Lake Charles. We actually use Polk radar to determine what's going on in Lake Charles, other than obviously walking outside and seeing what's going on. But from the, what's going on higher in the sky, we're not using the Lake Charles radar for what's going on in the city of Lake Charles itself. And so you think about that, same thing for local radars here at the TV stations. They're really not the best thing for the city of Lafayette itself. It's okay looking down at New Iberia, or okay looking over to Abbeville or over to Crowley. That's provided there's no rain occurring between here and Crowley, or here in Abbeville, or here in New Iberia. All right, vertically integrated liquid. VIL is a big tool that we use to estimate. Historically, we've used it to estimate hail sizes. There's been some corresponding things associated with it. when we have the pulse severe thunderstorms like this, there's just one little cell here, there's actually a good correlation between the VIL and the echotops to give you an estimate of what kind of wind speeds, because as the higher the storm cloud goes up in the sky and the higher the VIL, that just indicates if there's not much more of a mass 50,000 feet up in the air, well, that means odds are when that thing drops, got a better shot at creating stronger winds than if it's a smaller mass of water at 25,000 feet in the air. It's not going to make as much of a wind. So there is a correlation between VIL and echotops that we use to determine where the stronger wind scenarios are going to be. So like in this picture here, this storm here, northwest of Lake Charles. Lake Charles is kind of in both pictures here to the bottom right, looking to the northwest of us. That storm there looks much more impressive than the storm just due north of us with a lower VIL and a fairly decent echotop, but still the combination there is not nearly as good as this one here.